into the next part. And so the next part is using position time graphs to find acceleration. Now again, pause if you like, go through and copy down each term, and then we can start to go through each one of them. So when we talk about some of the terminology, there's this thing called the tangent technique. It's a method of determining velocity, and what we can do is we can break it apart, starting with a distance time, position time, displacement time graph, and we can keep drawing these little tangent lines. Now hopefully you've heard that word tangent before, but if not, it's not a big deal. All a tangent does is it touches a curve at one specific point. And so if we had a circle, for instance, a tangent line would come across and it would touch that circle at one specific spot. Okay, that's what tangents do. Okay, a straight line that touches a curve at a single point has the same slope as the curve at that point. Then we've got instantaneous velocity. We've talked about instantaneous speeds and velocities before. It just happens at that instant. So the graph that we're going to use to go through this looks like this. And it says that when analyzing position time graphs, most real-world situations, we don't really have steady lines and instead have these gradual inclines in speed. So what we're going to do is we're going to take a look at our graph and we're going to apply this idea of the tangent technique. Okay, because the line is curved in the picture, the slope always changes. It's not the same throughout the whole thing. But what we can do is we can use the tangent technique to find slopes at specific time intervals and get an idea of what's there. So the velocity at each specific time gives us what the instantaneous velocity is for that time interval. So if we take a look at where the stars are on our picture, the stars are the time intervals that we're going to focus on, but we're going to use the tangent technique and we're going to look at the points just outside of those stars and use those as straight lines, kind of like you can see in the example that's kind of already drawn in right there. So we're going to go to each star and we're going to draw a line that goes from point to point, okay, and see kind of how this changes. So we're going to take a look and find out what the speeds are at each of those points, and then we're going to plot them out. So let's kind of take a second and see if we can plot out a velocity time graph and see what the acceleration tells us about this. So right now we have a position time graph, it's distance time. The slope of a distance time graph is speed. Or position, I guess, because it's a direction in this case, is velocity. So let's take a second. We're going to plot out a couple of times. So if we go back and we take a look at where the first star is at 0.5 seconds. So that's the one that we're going to focus on up front, okay? At time equals 0.5 seconds. So when time is equal to 0.5 seconds, we're going to calculate the speed, okay, the average velocity, using a familiar equation that we had from before, df minus di over our change in time. So VAV is equal to, we need to go back and we need to see, okay, where is this position at the end? Right here, that's really close to 1, right? Half of 4 is 2 and it's in that lower quarter. So at 1 meter, and it starts at 0 meters. So this one is just 1 meter minus 0 meters. And all of that happens in 1 second, right? 1 to 0. So happens in 1 second. And if we subtract this through, we find that the average speed, 1 minus 0 is 1 divided by 1 second, is 1.0 meters per second. And the direction, if we take a look, was heading down. Okay, so that helps me find the speed at 0.5 seconds. Now, if you think you have a handle on this or an idea of what's going on, take a second and see if you can do 1.5, 2.5, and 3.5 seconds, and then come back and we can check it through and see if you're on the right track. So just pause, give it a try, and come back when you're ready. Okay, so if we keep going at time is equal to 1.5 seconds, then same thing as before, VAV is equal to dF minus di over top of our change in time. And so VAV is equal to, now if we take a look at 1.5 seconds, what we're finding is that it's at 4 meters per second minus 1 meter per second. And again, it's all over that same 1 second interval. Sorry, I wrote meters per second here, I just meant meters. Okay, 4 meters minus 1 meter, it's our position, over 1 second. So VAV, 4 minus 1 is 3, divided by 1 is 3 meters per second going downward. Okay, keep going from what we have. If we move on to 2.5 seconds, and we take a look at our speed, VAV, dF minus di again, over change in time. Then average velocity is equal to 9 meters per second minus 4 meters per second, all over top of 1 second. I did that again, sorry, this just should be meters. VAV, 9 meters minus 4 meters is 5 meters per 1 second. And again, heading downward. Okay, and really I guess I should say 5.0 to go along with what we've had. Our last one, time is equal to 3.5 seconds. So average velocity is equal to dF minus di again, over top of our change in time. And average velocity is equal to, we've got 16 meters this time for a position, 16 meters minus 9 meters. And so all of that again is still over that 1 second time interval. So our speed is equal to, in this case, 7.0 meters per second heading downward. So this gives us 4 separate speeds based on 4 separate time intervals. So if I take a look and we plot out where those speeds are matched up to our graph, we should be able to get a pretty good handle as to where these things are in terms of speed or velocity at the given time interval. So at 0.5 seconds, we were at 1 meter per second. So if you can pause, graph it out, come back, make sure you're on the right track, just so you can kind of try it out as well, and I'll just kind of keep moving through. So at 0.5 seconds, we're at 1 meter per second. 0.5 seconds, 1 meter per second. At 1.5 seconds, we're up to 3 meters per second. At 2.5 seconds, we're up to 5 meters per second. And at 3.5 seconds, we're up to 7 meters per second. So really, we can kind of see that this thing makes a line for us that we can use. So let's see if we can make our line go here. Start. And we're going to draw our line all the way through. Okay, so what we can see at the end is this thing goes up in a linear pattern, right? It keeps going up 2 over 2, up 2 over 2. And if we take a look at our numbers that we are using, 1 to 3 to 5 to 7, it just keeps going up by 2 meters per second each time. So that helps us graph out a velocity time graph. Now, after that, we know that the slope of a velocity time graph, because we've talked about this before, the slope of a velocity time graph, slope of a VT graph is acceleration. So if I can find the slope of this line, I know what the acceleration is at each of those time intervals. Now, luckily, the slope of the line, that doesn't change very much, right? What does this tell us about the acceleration? And then to make an acceleration time graph over the same time interval. So, start with the first part. What does this tell us about the acceleration? Well, the acceleration is increasing, but the velocity is increasing at a steady rate. It's uniform motion, which means as this is increasing, the acceleration is held steady. At any point along this line, I can find the slope, and that slope should be the same. So if I look at the very end here and use our acceleration equation that we have from before, okay, AAV, VF minus VI over T. Pick any time period here and figure out VF minus VI over T. The easiest one to do is to pick the end and the beginning. If I pick the end, our end point up here I can see is 8 meters per second, and our beginning point is 0 over top of 4 seconds. And then I can find that the average acceleration is going to work out to be 2 meters per second squared, still with that same direction heading down. So I can figure out slope at any point here, 6 divided by 3, 4 divided by 2, 2 divided by 1. They all give me the exact same value. Okay, they all give me this 2 meters per second squared. So if I were to plot out 2 meters per second squared consistently over that time interval, what would it look like? Well, it would, at 1 second, it would be at 2 meters per second. At 2 seconds, it would be at 2 meters per second. At 3 seconds, still 2 meters per second. And at 4 seconds, still at 2 meters per second. For each of those time intervals, I'm getting the exact same slope from that velocity time graph that we looked at from before. So if I take a look here now, I can draw a straight line through this. Okay, going straight across. And we can kind of see a graph of acceleration time. Okay, so that's how I can get from distance or position time, okay, a position time graph, through to an acceleration time graph using the tangent technique. Now that's one of 2 types of questions that I could ask you guys to solve for. Okay, it's kind of moving forward. It's acceleration and time at the end, right? We start it with position time, we get to acceleration time.